Alright, hello everybody and welcome to the first video of the first module of the kind of mini unit that comes after Unit 3. So before we get into the specifics, a little bit about this kind of mini unit. There is no specific exam that is attached to this material. It will be on the final, but it doesn't get its own designated exam. The reason why, if I do it the other way, you wind up basically taking two tests back to back, and you wanted the first one back before the final exam happens anyway. So to allow you to have feedback on every single unit exam, I add a little space between that exam and the final, and in that time we cover this extra material where we discuss correlation and regression, which we're going to be beginning with today. So a little bit of basics on correlations and a little bit on regression as well. These two modules we treat them separately, but they are very closely related. We've talked about correlations a few times. We talked about it back in method, and it's come up a few times since then as well. But a correlation is a correlation. It's the relation between two variables, or more, but two at the very simplest level. So correlation is a statistical technique that we use in order to figure out if two variables are related, to what degree they're related, and in what direction they're related in. So this is a very powerful way of very simply representing how two variables appear to be linked. As scores on one variable change, do they tend to change on the other, and if so, in which direction? Some examples here. You could measure people's sugar consumption and the amount of physical activity they engage in and correlate them. See if there's a consistent relationship there, if they tend to move in tandem or not. You would probably expect here what's called a negative correlation, where more sugar consumed is related to less physical activity. IQ and annual income, you could measure both of those and see if they're related to one another or not. Here you probably expect a positive correlation, where people that have higher IQs tend to make more money and vice versa. By the way, real world data, there is a positive correlation there, but it's not nearly as strong as you might expect, a lot weaker than you'd think. More intelligent people do tend to make more money, but not dramatically so. And last, you could measure people's engagement with course material. So kind of how involved they are, how active they are in sort of working with that material and reviewing it, how low distraction their studying is, etc., etc., all things that involve being focused on what you're doing, and their grade in the course. You could correlate those two things as well. I've charted something that looks exactly like that back here. This is first what's called a scatter plot, which we'll see quite a bit of very soon. And also we have a dotted line there, which kind of describes how these two variables are related. So the individual dots might be people's scores on these engagement and grade variables, and then the dotted line reflects their average relationship with each other. Now these variables are typically identified as x and y, and down here on our horizontal axis, that's what's generally called our x variable. Here on our vertical axis, we generally chart out our y variable. More on that to come in the next couple of videos. But here's the big advantage. This dotted line here not only describes the relationship between those two variables in our data set, how they're sort of typically linked to one another, but we can also use it in that kind of powerful way of predicting things that haven't happened yet, or scores that we just don't know. So if I know the average relationship between engagement with material and grade, and I know just one of those, either your grade or your level of engagement, I can predict with some accuracy your level of the other. I can even predict things that haven't even happened yet. I can predict people's final grades based on things that have happened early in the semester. I can't find causality, so I can't find cause and effect. I'm just describing relationships here. I don't know which one comes first or which causes the other, or even if either of them cause each other. But a correlation can sometimes provide some hints at cause and effect relationship. We can actually use some techniques to eliminate some possible causal relationships, but with correlations you never can confirm one. So that key phrase, correlation doesn't equal causation, it's accurate. It's a little more complicated than that. We can get some evidence that's consistent with some causal relationships. We can rule some causal relationships out, but we can't ever, with just a correlation, confirm one exact pattern of cause and effect. So there are ways of sidestepping that correlation causation problem, but there's no way of fully getting past it. Anyway, the big thing we're using correlations for here is to describe the nature of our relationships, and then eventually in the next module to use that information to make predictions about unknown scores. So here's a basic breakdown. We already kind of hinted about that. Correlation determines whether or not Variables or distributions of scores are linked, whether they're related. Correlations, when you calculate them, or even when you visualize them, will tell you information on the nature of the relationship, what direction it goes in, and how strong that relationship is. How consistently do those two variables tend to move together. You have to measure 2 or more variables for each participant to get a correlation. When calculating a correlation, I got to measure 2 separate variables. Notice this is different from within participants design, where we are measuring each participant multiple times, but always on the same DV. Here we're measuring multiple variables and relating them to each other instead of measuring the same dependent variable multiple times under different circumstances and comparing them. So what can we do with this sort of thing? Well, say I'm an admissions officer, I might be interested in those standardized tests that everybody has to suffer through and how it relates to how students actually do in college, especially in their first year when they've just kind of entered school. I might calculate a correlation coefficient, this little R statistic here, that might describe how strong the relationship is and in what direction the two are related. And here we see it's a positive correlation. People that do better on the ACTs tend to have higher GPAs in their first year than people that do worse. It's not destiny, it doesn't happen to every single person, but on average, there's a link there. Eventually, and in the next module, what we'll be doing is learning how to use correlations to create what are called regression frameworks. Regression frameworks let us use correlations and leverage that information to make predictions. Predictions of values that we don't have yet, scores that we don't have, people we haven't measured, or even things that haven't happened yet. It's a way of sort of predicting the future, albeit imperfectly. We can predict things that haven't happened yet. So we take that correlation one step farther, we create what's called a regression line or a line of best fit, something like the dotted line back here. And we can, again, take that information and say, okay, if I know Jimmy's score on his should be ACTs, what would I predict his first year GPA will be? I might get a predicted score on the Y variable, that's the little hat means, of 3.22. Say Jimmy did pretty well on his ACT, his predicted first year GPA is going to be pretty high. So I'm predicting something that hasn't happened yet. Again, Jimmy's not in school yet, he doesn't have a GPA, but I'm using my knowledge of that relationship to make predictions of scores that I don't have. So again, this is one of the ways that we can do some powerful things with these correlations. We can predict things that haven't happened yet with some accuracy. One last point before we move on. There are, just like there are lots of different types of ANOVAs and t-tests, there are lots of different types of correlations we can calculate. Fortunately for us, one of them is used much more often than all the rest of them put together, and we're going to focus on that one. So what type of correlation you use depends on what type of variables you're dealing with. Here we see our X variables, here we see our Y variables, and we have kind of a grid here of what test you would use for each combination. And notice here we see the names of some of our scales. Nominal scales, ordinal scales, quantitative, which means interval or ratio. Remember we talked about a lot of tests rely on having at least an interval scale for the variable you're measuring. It's true of our common correlations as well. So something about this chart, do not memorize the names of all of these correlations. That's not important. That's not something I'm going to test you on. But do be aware that the correlation we're talking about, Pearson's R, requires both variables being interval or ratio. There are other correlations you can conduct when you have different types of scales for one or both variables, and you can see the names of them here. But overall, the Pearson's R is the one that we're going to be calculating. So be familiar with what the conditions are under which we can calculate Pearson's R, and then just for the rest, just know that there are other correlations that can be calculated. Don't worry about exactly what their names are, but just know that there are ways that we can account for that. All right, that's the end of this introductory video. Next up, we're going to talk a little bit about how to make sort of thing that's over here, a basic scatter plot, a way of visualizing your data and representing the patterns in that data set. See you then.